Welcome to Universe Orbit, your gateway to exploring the vast wonders of space, where the mysteries of the cosmos unfold through captivating videos. Don't forget to subscribe so you never miss a single voyage through the infinite universe. Jupiter sits in the tapestry of the sky like a sovereign draped in swirling robes, its presence both majestic and mysterious. For millennia, humans have looked up and noticed this bright, steady point of light moving against the backdrop of stars, naming it after gods and kings, weaving stories about its influence, and slowly learning that it is not a star at all, but a colossal world whose scale and complexity dwarf everything else in the solar system. Jupiter is more than the largest planet. It is a dynamic, restless giant whose gravity sculpts the architecture of the planetary system and whose storms and magnetic might reveal extremes of physics, chemistry, and planetary behavior. To understand Jupiter is to confront the extraordinary, how a world born from the same disk of gas and dust as Earth could grow into an immense, mostly gaseous realm, how turbulent storms persist for centuries, how a magnetosphere can carve out a bubble in the solar wind larger than the sun, and how a retinue of moons can together host oceans, cryovolcanism, and subtle clues about habitability. This exploration will carry the reader from Jupiter's place in planetary formation theories to the textures of its atmosphere, from the choreography of its moons to the human missions that have extended our knowledge far beyond what naked eye gazes could reveal. At first glance, Jupiter may seem simple, a hazy orange ball, banded and spotted, dominated by an oval storm called the Great Red Spot. But its apparent simplicity is deceptive. Jupiter's radius is more than 11 times that of Earth, and its mass is more than 300 times greater. The planet's composition is primarily hydrogen and helium, the lightest elements, arranged not as a thin atmosphere over a solid surface, but as a gradual transition from gaseous outer layers to denser, fluid inner regions, and finally to an uncertain, possibly metallic core. Deep within, under crushing pressures and blistering temperatures, hydrogen behaves in exotic ways, becoming metallic and conducting electricity. This metallic hydrogen is central to Jupiter's dynamo, the engine that generates an immense magnetic field. The core itself may be a compact mixture of heavier elements, perhaps composed of rock and ice, but recent models suggest it could be diffuse, partially eroded, or blurred into the surrounding envelope, a sign that the early history of Jupiter was violent and transformative. Jupiter's formation story is entwined with the earliest chapters of the solar system. Out beyond where the terrestrial worlds assembled, the protoplanetary disk contained abundant ices and dust, and the pressure and density conditions there allowed a planetary embryo to grow quickly. One favored model posits that Jupiter began with the accretion of a heavy element core, large enough to gravitationally capture surrounding hydrogen and helium from the disk. Once a threshold mass was crossed, runaway gas accretion ensued, and the planet ballooned in size, gobbling gas while the disk still existed. The timing of that growth is crucial. Jupiter likely formed early, perhaps within a few million years of the Sun's birth, and its early gravitational reach likely influenced the distribution of other building block hooks, scattering or shepherding material that would later become asteroids, comets, and maybe even influence the formation of the inner terrestrial planets. In this sense, Jupiter is both a product of and an agent in solar system formation, a nexus where early chemistry and dynamics converge. The visible face of Jupiter is dominated by bands of clouds that encircle the planet, alternating dark belts and bright zones that arise from complex atmospheric circulation. These bands are driven by powerful east-west jet streams, with wind speeds in some regions exceeding hundreds of kilometers per hour. Within and between these jets shear and mix, creating eddies, vortices, and waves. The Great Red Spot, an immense anticyclonic storm larger than Earth, has swirled for centuries and offers a window into long-lived atmospheric structures. Its reddish hue is still the subject of investigation and may derive from complex organic molecules, phosphorus or sulfurous compounds that have been chemically altered by sunlight and charged particles. Smaller ovals and white spots pepper the global canvas, some forming from the breakup of larger storms, others merging into larger features. Vertical structure matters too. Ammonia and water vapor condense at different altitudes, forming distinct cloud layers, and storms can dredge up material from deeper layers, revealing chemical signatures that speak to the planet's deeper composition. Beneath the clouds, pressures and temperatures grow dramatically. The visible cloud deck sits at relatively low pressure compared to deeper layers. Descend further, and hydrogen transitions into a fluid state, then a metallic state, where electrons become delocalized and electrical conductivity soars. This metallic hydrogen is probably in motion, convecting and rotating, creating electrical currents that feed the dynamo. Unlike Earth, where a solid inner core and liquid outer core rotate together to produce a magnetic field, Jupiter's dynamo operates in a highly turbulent, rapidly rotating fluid environment. The result is a magnetic field that is not only strong, but complex. Jupiter's magnetosphere, the region of space controlled by its magnetic field, is a giant magnetic bubble that extends millions of kilometers into space, sweeping up charged particles and forming radiation belts that are orders of magnitude more intense than Earth's Van Allen belts. These belts make the space near Jupiter a dangerous place for spacecraft and any hypothetical explorers. But they also drive spectacular interactions with the moons and the surrounding plasma. The interaction between Jupiter and its moons is one of the most enthralling aspects of the system. Jupiter's four largest moons, Io, Europa, Ganymede, and Callisto, discovered by Galileo Galilei in the early 17th century, are worlds in their own right. Io is a riot of volcanism, the most geologically active body in the solar system, driven by tidal heating as Jupiter's gravity flexes the moon's interior. Lava flows, sulfurous plumes, and a constantly changing surface mark Io as a furnace. Europa presents a different, tantalizing prospect, an icy shell overlain on a global ocean. The surface is crisscrossed with lines and ridges, evidence of a dynamic ice shell with possible exchange between the surface and subsurface ocean. Beneath Europa's frozen crust, a salty, rocky seafloor, heated by tidal forces and perhaps hydrothermal activity, could create conditions suitable for chemical gradients and, conceivably, for life. Ganymede, the largest moon in the solar system, is itself a small planet with a differentiated interior and its own intrinsic magnetic field, a remarkable exception among moons. Callisto is a heavily cratered testament to a less geologically processed surface, preserving a record of impacts and the ancient environment of the outer solar system. Beyond the Galilean moons lies a host of smaller satellites, irregular captured bodies and ringlets whose origin stories range from collisions to captured fragments. Jupiter's magnetospheric interactions with its moons create phenomena both violent and beautiful. Io's volcanoes spew ions into space, forming a torus of plasma that co-rotates with Jupiter's magnetosphere and feeds powerful auroras when particles spiral along field lines into the planet's polar regions. These auroras are more than mere light shows. They are diagnostic of the magnetospheric dynamics and the coupling between the planet and its satellites. Energetic particle bombardment also alters surfaces and atmospheres. Europa's tenuous atmosphere is maintained by surface sputtering, and the interplay between magnetospheric particles and the ice shell drives chemistry that can be investigated by future missions. In short, Jupiter is not an isolated world. It is at the heart of an interactive, interdependent system in which satellites, rings, plasma, and the planet's magnetic personality are inseparable. Rings may not be the first thing people associate with Jupiter, but the planet does possess a faint ring system. Compared to the broad, bright rings of Saturn, Jupiter's rings are subtle, made of small particles probably produced by micrometeoroid impacts on small inner moons. These particles form a thin disc-like structure, detectable by spacecraft and sensitive telescopes, and they round out the portrait of Jupiter as a planet with diverse expressions of planetary physics, from colossal storms to delicate rings. The study of Jupiter has been as much an observational revolution as a scientific one. Early telescopic observers noted the planet's moving moons and banded appearance, but it was only in the space age that the veil began to lift. Flybys and orbiters have visited and studied Jupiter, each mission a leap in understanding. Pioneer and Voyager missions provided first close-up glimpses, mapping magnetic fields, radiation belts, and the large-scale structure of the atmosphere. The Galileo orbiter, which arrived in the 1990s, dropped a probe into Jupiter's atmosphere, measured compositions, and studied moons in greater detail, revealing the complexity of the system. More recently, the Juno mission has orbited Jupiter along a highly elliptical path, diving in close over the poles to map the gravity field, probe the deep atmosphere with microwave instruments, and study the magnetic environment with unprecedented precision. Juno's discoveries have been revelatory. It has shown that Jupiter's interior may be more heterogeneous than once thought, with deep atmospheric flows and gravity anomalies pointing to complex internal structure. The planet's poles display weather patterns unlike those in equatorial regions, including clusters of cyclones arranged in geometric patterns. Juno's instruments have also revealed peculiarities in the magnetic field, suggesting small-scale structures and temporal variations that challenge previous dynamo models. Alongside spacecraft, Earth-based and space telescopes continue to monitor Jupiter. Long-term monitoring is crucial because Jupiter's atmosphere is a dynamic laboratory where processes evolve over months, years, and centuries. Storms grow, merge, and decay. The Great Red Spot changes in size and color. Waves propagate through the belts, and interactions with the solar wind and magnetosphere modulate auroral activity. These temporal scales mean that each mission and observation adds a snapshot to a larger, evolving narrative. And only by stitching these snapshots together can scientists hope to understand processes that unfold both rapidly and slowly. Beyond the immediate scientific fascination, Jupiter plays a profound role in shaping how we think about habitability and life elsewhere. While Jupiter itself is a gas giant with no solid surface and extreme conditions hostile to life as we know it, several of its moons are leading targets in the search for environments that could support life. Europa's subsurface ocean stands out as one of the most compelling places to search for biology beyond Earth. The possibility of liquid water, energy sources from tidal heating, and chemical exchanges with the surface set the stage for astrobiological inquiry. Even Io, though seemingly inhospitable, teaches us about the energy flows that can drive chemical processing and the diversity of planetary outcomes. Studying these moons expands our conception of habitable niches and informs the design of future missions aimed at detecting biosignatures. Human curiosity has always been the force behind our missions to Jupiter, but exploration faces profound technical challenges. Jupiter's intense radiation belts pose a risk to electronics and instruments. The deep gravity well requires significant energy for insertion and orbiting maneuvers, and the distance from the Sun limits available solar power, complicating mission design. Radioisotope thermoelectric generators have been crucial for powering deep space missions where solar flux is weak. In spite of these hurdles, the scientific return has justified the effort, and future missions are being designed to push the boundaries further. Proposals and planned missions aim to explore icy moons more extensively, to deliver landers or cryobots that could penetrate ice, to return samples, and to study the planet itself with instruments capable of probing ever deeper into its atmospheric and interior secrets. Jupiter's cultural and historical imprint is also significant. Across civilizations, bright planets have been associated with gods of thunder and sky, and Jupiter's prominence in the heavens made it a symbol of kingship and power. Modern culture continues to draw on these associations. Jupiter appears in literature, film, and the arts as a motif of grandeur or the unknown. Scientific understanding has transformed our image of Jupiter from a godlike presence to a complex world governed by physics. But that same wonder persists in the face of new discoveries. Observing Jupiter with even modest amateur equipment remains gratifying. Telescopes of modest aperture reveal the banded structure, the Great Red Spot, and the Galilean moons in their eternal dance. Time-lapse observations capture the motion of cloud features and the transits and shadows of moons across the planetary disk. Through backyard observations and global networks of amateurs and professionals, continuous monitoring is possible, allowing humans everywhere to participate in documenting changes in real time. As we look forward, Jupiter remains both a challenge and an opportunity. It is a testbed for planetary science, a laboratory for extreme atmospheric physics, and a system whose moons may harbor the ingredients for life. Unanswered questions persist. What is the true nature of Jupiter's core? How do deep atmospheric flows connect to the surface phenomena we observe? What drives the peculiarities of its magnetic field? How do the interactions between Moon and planet evolve over billion-year timescales? Each question invites new missions, new instruments, and new ideas. The story of Jupiter is not a finished tale, but an ongoing conversation between observation, theory, and exploration. It is a reminder that planets are not static ornaments, but living systems with histories and dynamics. From the first telescopic sketches to the detailed gravity maps beamed back by modern orbiters, our understanding of Jupiter has deepened, and with every advance we discover new layers of complexity. The planet's role in the solar system exemplifies how a single body can influence an entire planetary neighborhood, sculpting trajectories, shaping atmospheres, and nurturing moons that might, in the quiet depths beneath their ice, harbor secrets as profound as our own origins. To stand beneath the night sky and look toward Jupiter is to peer at a world that has been at the center of human wonder for centuries. It is to confront extremes of scale, energy, chemistry, and time, and to be humbled by the fact that even our most powerful instruments yield only partial knowledge. Yet that partial knowledge is rich. It tells of storms that persist for centuries, of moons with oceans hidden beneath ice, of magnetic realms that dwarf planetary dimensions, and of a planet whose early growth played a decisive role in crafting the architecture of our solar system. Jupiter teaches us to think big, to expect the unexpected, and to cherish the interplay of curiosity and engineering that brings a distant world within the grasp of human understanding. In the long arc of exploration, Jupiter will continue to be a destination for ambitious missions, an object of curiosity for telescopes and theorists, and a subject of inspiration for those who wonder about the cosmos. Its storms will continue to dance, its moons will keep their hidden rhythms, and its magnetosphere will remain a roiling sea of charged particles. From the perspective of a planet much older than humanity, our efforts are a brief, bright inquiry. Yet those inquiries matter. Through them we learn not only about a distant gas giant, but about the processes that shaped worlds, about the potential ubiquity of oceans and niches for life, and about the nature of planetary systems in a universe filled with stars and planets of every imaginable variety. Jupiter invites us to explore, to question, and to imagine, and in doing so it remains firmly, magnificently, the king of the planets. Jupiter's story continues deep within its immense atmosphere, where sunlight fades and pressure rises to levels that defy intuition. In these hidden layers, the concept of a surface becomes meaningless, replaced by a gradual transition into denser and hotter states of matter. Hydrogen molecules that drift freely in the upper atmosphere become compressed into a thick fluid, and eventually, under pressures millions of times greater than Earth's sea level pressure, the hydrogen atoms are forced so close that electrons detach and begin to move freely. This sea of metallic hydrogen conducts electricity and forms a vast churning interior where heat flows outward from Jupiter's internal reservoir. The heat is a remnant of formation, leftover energy from the collapse of the original gas envelope. Jupiter still radiates more energy into space than it receives from the sun, a sign that the giant planet's interior is cooling only slowly across billions of years. Heat distribution inside Jupiter drives convection, creating deep atmospheric currents that influence what we observe at the cloud tops. Unlike Earth's atmosphere, which is thin relative to the planet's size, Jupiter's atmosphere constitutes a significant fraction of the planet's volume. Convection columns may span thousands of kilometers, rising and sinking in patterns influenced by rotation and magnetic forces. These convective motions shape belts and zones, powering storms that can reach astonishing vertical extents. Lightning flashes detected by spacecraft reveal electrical discharges far stronger than those on Earth, suggesting extensive convection and complex interactions between ammonium hydrosulfide clouds, water clouds, and deeper layers. Such processes make Jupiter an unparalleled natural laboratory for the study of atmospheric electricity and fluid dynamics. Rotation plays a crucial role in Jupiter's atmospheric behavior. The planet completes one rotation in just under 10 hours, making it the fastest spinner in the solar system. This rapid rotation dramatically enhances the Coriolis effect, causing the formation of stable jet streams and reorganizing convection into the banded structure we recognize. The belts tend to be warmer and darker, areas of descending air, while the zones are lighter and cooler, areas of rising air. These patterns persist yet evolve subtly over time, producing a combination of long-term stability and short-term variability. Observers have noted that some belts periodically fade or brighten, likely due to changes in aerosol concentrations or vertical wind shifts. These variations hint at deeper cycles within Jupiter's meteorological engine that remain only partially understood. The Great Red Spot, Jupiter's most iconic feature, demonstrates the extraordinary persistence of Jovian storms. This swirling vortex, larger than Earth, rotates counterclockwise in the southern hemisphere and maintains winds that reach tremendous speeds. Though centuries old, the Great Red Spot has shown signs of change in recent decades, shrinking in sound, altering shape, and occasionally shedding smaller vortices. The underlying mechanisms governing its longevity remain a matter of scientific inquiry. Perhaps deep energy sources feed it, or surrounding jet streams stabilize it. Perhaps its altitude allows it to tap into differential rotation that sustains its motion. Whatever the case, it stands as a symbol of planetary dynamism and a reminder that alien atmospheres can host features far more powerful and enduring than what we see on Earth. Jupiter's weather systems extend beyond the Great Red Spot. White ovals, brown barges, filamentary storms, and ephemeral plumes emerge across the globe. Some storms erupt from deep layers, breaking through cloud decks and producing bright outbursts observable even from Earth-based telescopes. These superstorms can reshape entire belts. Waves propagate along the boundaries of jets, forming ripples and patterns that reveal invisible physics beneath the cloud tops. When viewed through infrared instruments, the planet reveals hot spots and cold regions, showing the dynamic interplay between heat flow, chemical composition, and atmospheric motion. UV observations expose auroral features that shift in response to solar wind pressure and magnetospheric particle streams. All this complexity points to Jupiter as more than a gas giant. It is a dynamic sphere of physics in motion. Much of the fascination comes from the ways in which Jupiter provides analogs and contrast to exoplanets discovered around distant stars. Many exoplanets are gas giants, some even larger than Jupiter, orbiting far closer to their stars in configurations unknown in our solar system. By studying Jupiter's atmosphere, magnetic field, and internal structure, scientists gain critical reference points for interpreting observations of these distant worlds. Jupiter's chemistry, ranging from ammonia and methane to complex hydrocarbons, becomes a benchmark for understanding what spectral signatures might mean elsewhere. The dynamics of belts and storms on Jupiter offer clues to what weather systems might look like on exoplanets with different temperatures or rotation rates. In this sense, Jupiter serves as both a neighbor and an ambassador, linking our solar system to the broader galactic population of giant planets. While Jupiter's atmosphere is a world of storms, its interior remains a frontier of speculation and inference. Gravity measurements from the Juno mission have revealed anomalies that suggest deep-seated flows extending thousands of kilometers into the planet. These flows may be responsible for transporting angular momentum and influencing the magnetic field. The gravity field also hints at a diluted core, a region where heavy elements are not concentrated in a single compact core, but are instead mixed with hydrogen and helium across a large inner volume. Such a structure challenges traditional models of planet formation and suggests that Jupiter may have undergone a major collision early in its history, disrupting its core and blending heavier materials into its envelope. If such a collision occurred, it would have been one of many violent events during the chaotic youth of the solar system. Jupiter's magnetic field, one of its most extraordinary attributes, continues to surprise scientists, strong enough to deflect the solar wind far upstream and carve out a magnetic bubble in space. It includes zones of intense radiation capable of damaging electronics and posing hazards to spacecraft. The magnetic poles are not symmetrical or aligned neatly with the rotation axis, instead showing a patchwork of positive and negative regions that imply unusual dynamo behavior. Juno's mapping of the magnetic field has revealed a concentrated region dubbed the Great Blue Spot, a magnetic anomaly near the equator that appears to be drifting over time. Understanding this drifting and the underlying dynamo action could shed light on how magnetic fields arise and evolve in planets, brown dwarfs, and stars. Jupiter's auroras, fed by both solar wind particles and material from Io's volcanic eruptions, glow intensely in ultraviolet and infrared wavelengths. Unlike Earth's auroras, which depend strongly on solar activity, Jupiter's auroras are partially governed by internal magnetospheric dynamics, particularly the exchange of particles between the moons and the magnetosphere. Io, with its prodigious volcanic output, spews sulfur dioxide that becomes ionized and trapped in Jupiter's magnetic field, creating plasma that interacts with both Jupiter and the Moon system. These interactions generate electric currents along magnetic field lines, producing auroral footprints corresponding to Io, Europa, and Ganymede. Each moon effectively stamps its presence onto Jupiter's polar lights, a kind of electromagnetic signature encoded into the auroral glow. The moons themselves form an intricate family whose dynamics and evolution are shaped by Jupiter's gravity. Io's orbit, slightly eccentric due to resonance with Europa and Ganymede, subjects it to tidal flexing that generates intense internal heat. This heating powers Io's volcanism, which in turn influences the plasma environment. Europa's position in the resonance chain means it too experiences tidal forces, though less extreme. These forces keep its subsurface ocean warm and possibly active. Ganymede uniquely interacts with Jupiter not only as a satellite, but also as a magnetic partner. Its intrinsic magnetic field carves out a mini magnetosphere within Jupiter's much larger one. This dual magnetosphere system is unlike anything else in the solar system and provides an opportunity to study magnetic interactions on scales rarely accessible. Beyond the Galilean moons, dozens of smaller moons orbit Jupiter in complex patterns. Many of these irregular moons follow eccentric, inclined, or retrograde orbits, suggesting that they are captured asteroids or fragments of larger bodies disrupted long ago. Their distribution and composition offer clues about the population of small bodies in the early solar system and the gravitational perturbations that shape their fates. Collisions between these small moons likely created shrapnel that continues to orbit today, and some of this debris may contribute to Jupiter's faint rings. Jupiter's rings, though often overlooked, represent an important chapter in its story. Composed mostly of tiny dust particles, these rings are thought to arise from impacts on small inner moons. They are dynamic structures, constantly replenished and eroded as dust spirals inward under drag forces or is knocked away by electromagnetic interactions. Studying Jupiter's rings provides insight into ring formation processes common across the solar system, from the majestic rings of Saturn to the tenuous arcs of Neptune. These rings show that even in the outer solar system, where giant planets dominate, delicate structures can persist. Human missions to Jupiter have broadened our understanding dramatically, yet each mission also reveals new mysteries. Future missions aim to probe deeper, particularly into the icy moons that may harbor subsurface oceans. A spacecraft dedicated to exploring Europa, equipped with ice-penetrating radar and high-resolution instruments, could reveal the thickness of the ice shell, the nature of the ocean beneath, and potential sites where exchange between the surface and ocean occurs. If plumes of water vapor exist, as hinted by some observations, a mission could sample them directly without drilling through ice, offering an unprecedented opportunity to search for signs of biological activity. Jupiter's environment challenges spacecraft engineering. Radiation can degrade electronics, solar power is limited, and fuel requirements are steep due to the planet's deep gravity well. Engineers must design trajectories that limit exposure to radiation, shield critical components, and conserve energy. Juno, for example, uses a highly elliptical polar orbit to minimize time spent in intense radiation belts. These constraints influence mission duration, available instruments, and data transmission. Despite the challenges, every mission to Jupiter delivers scientific treasure. As astronomers observe Jupiter, they often consider its role in the broader story of planetary systems. Jupiter may have acted as a barrier that protected the inner solar system from excessive bombardment, or it may have disrupted early planetary embryos. Some models propose that Jupiter migrated inward early in its history, potentially influencing the distribution of material that formed Earth. The degree to which Jupiter shaped the inner planets affects our understanding of Earth's formation and the conditions that made life possible here. By studying Jupiter's early evolution, scientists hope to understand not just a distant giant, but also the pathways by which habitable worlds arise. Jupiter's cycles, storms, magnetic pulses, and moon interactions remind us how dynamic a single planet can be. This dynamism also shapes its influence on solar system stability. The gravitational pull of Jupiter affects comets and asteroids, sometimes deflecting them toward the inner solar system, other times ejecting them entirely. Its immense mass acts as both protector and disturber, altering orbital paths and shaping the architecture of the solar system. Long-term simulations of planetary motion show that Jupiter's presence helps stabilize Earth's orbit, contributing indirectly to the environment in which life flourished. As exploration continues, scientists envision instruments capable of probing deeper into Jupiter's atmosphere. A future probe might descend into the planet for hours, measuring composition at various depths, analyzing cloud layers, and capturing high-fidelity data from regions unreachable by remote sensing. Floating balloon platforms could drift in the atmosphere, sampling winds and aerosols, sending back continuous data. Such missions would answer lingering questions about water abundance, atmospheric mixing, and the nature of deep storms. In pondering Jupiter's grandeur, humans also reflect on the emotional and cultural impact of encountering such a world. The sheer scale of Jupiter, its storms larger than continents, its moons like miniature planets, its magnetic domain stretching millions of kilometers, invokes a sense of awe that transcends scientific curiosity. It reminds us of our place in the cosmos, small yet capable of perceiving, understanding, and exploring. Artists, writers, and philosophers have drawn on Jupiter's presence as a symbol of power, danger, mystery, and beauty. The tradition continues as modern imagery from spacecraft inspires new generations to look upward and imagine worlds beyond our own. Even the simple act of watching Jupiter rise can inspire. Through a telescope, the rings of Saturn may dazzle, but the Galilean moons offer something special: visible movement. Over the course of a night, the moons shift position, casting shadows on the planet or disappearing behind it. Their motion reveals celestial mechanics in action, a cosmic dance choreographed by gravity. For many amateur astronomers, observing Jupiter is a gateway into a lifelong interest in astronomy, astrophysics, and planetary science. As research pushes forward, Jupiter stands as both a complex challenge and an enduring icon. Scientists study its chemistry to understand atmospheric processes relevant to planets across the galaxy. They model its magnetic field to improve dynamo theories. They analyze moon interactions to uncover clues about ocean worlds. Each new discovery adds depth to our understanding of planetary systems and reminds us that the solar system is far from static. It is a dynamic, interconnected collection of celestial bodies whose histories and futures are entangled. Ultimately, Jupiter is not simply a giant ball of gas. It is a narrative bow of cosmic evolution. It is a relic of solar system formation, a sculptor of planetary destinies, a host of moons that may harbor life, and a beacon for scientific discovery. Its storms roar, its magnetic field pulses, its interior churns, and its moons whisper stories of ice, fire, and water. To write about Jupiter is to write about the forces that shape worlds, the mysteries that drive exploration, and the human desire to understand the universe. Jupiter's influence extends far beyond the boundaries of its immediate environment, shaping the trajectories of countless small bodies that drift through the solar system. Comets that plunge inward from distant reservoirs such as the Oort cloud or the scattered disk often pass near Jupiter, where its enormous gravity can alter their orbits dramatically. Some comets are captured into shorter period orbits, becoming part of the family of Jupiter comets that regularly return to the inner solar system. Others are slingshotted outward, ejected entirely from the solar system, becoming interstellar wanderers. This gravitational filtering effect contributes to the long-term stability of Earth's environment by reducing the number of potentially hazardous objects that might otherwise collide with the inner planets. Yet Jupiter can also redirect comets and asteroids inward, demonstrating its dual role as both guardian and disruptor. Asteroids too bear the imprint of Jupiter's presence. The main asteroid belt, located between Mars and Jupiter, shows clear evidence of gravitational sculpting. Gaps within the belt, known as Kirkwood gaps, correspond to orbital resonances with Jupiter, regions where gravitational nudges accumulate over time and remove objects from those orbits. These resonances can destabilize asteroids, sending them into planet-crossing orbits that may eventually approach Earth. Meanwhile, Jupiter's Trojan asteroids, two large swarms occupying the stable Lagrange points ahead of and behind the planet, are remnants of early solar system formation. These Trojan bodies form vast clouds of diverse composition, from rocky fragments to objects that appear more comet-like, offering clues about the primordial disk that gave birth to the planets. The stability of the Trojan swarms speaks to Jupiter's deep gravitational influence and may hold secrets about the early solar system's migration history. Some theories propose that Jupiter and Saturn migrated outward after forming, interacting with the disk of leftover planetesimals, and altering their own orbits in the process. These migrations could explain the distribution of small bodies today and the presence of Trojans captured during chaotic exchanges. Jupiter's early wanderings may have stirred the inner solar system and influenced the formation of terrestrial planets, affecting everything from their sizes to their water content. Studying Jupiter's Trojans may help reconstruct this ancient migration and reveal how common such migrations might be among exoplanetary systems. Jupiter's connection to exoplanet research that continues to grow. The discovery of hot Jupiters, gas giants larger than Jupiter, orbiting blisteringly close to their stars, challenged earlier assumptions about planetary system architecture. Jupiter's current location, far from the Sun, suggested that giant planets form in cold regions where ices can condense, providing material for rapid growth. But the existence of hot Jupiters forced scientists to consider the mobility of planets after formation. Jupiter's structure, composition, and dynamical effects provide essential reference points for interpreting these exoplanet observations. By understanding how Jupiter formed and migrated or remained relatively stable, astronomers can better predict how common Earth-like planets might be in systems with giant planets. Jupiter's chemical makeup also provides key insights into cosmic evolution. Measuring the abundance of heavy elements in Jupiter helps scientists infer the composition of the solar nebula from which the Sun and planets formed. Juno's instruments have detected elevated levels of certain elements, such as nitrogen and carbon, compared to the Sun. These enrichments imply complex processes during the planet's formation, perhaps involving the accretion of icy planetesimals or the incorporation of material from distant regions of the protoplanetary disk. If Jupiter accumulated significant amounts of such material, it would suggest that the early solar system was more dynamic and interconnected than once believed, with mixing processes carrying material across vast distances. The deep atmosphere of Jupiter remains a scientific frontier. Unlike Earth, where sampling the atmosphere is relatively straightforward, Jupiter's extreme conditions make direct measurements difficult. Yet the insights gained from probes, spectroscopy, and remote sensing continue to reveal new layers of complexity. Water abundance, for example, is a crucial parameter for determining Jupiter's formation history. Water resides deep within the atmosphere, and only the most capable instruments can detect its signature. Juno's microwave radiometer has provided unprecedented data on water concentration, suggesting variations by latitude and depth that point to large-scale atmospheric circulation patterns. These findings challenge earlier assumptions and refine our understanding of how giant planets mix heat and material. Cloud formation on Jupiter presents another area of intrigue. Ammonia clouds form the highest visible layers, creating the white regions that contrast with the darker belts. Beneath these lie ammonium hydrosulfide clouds, and deeper still reside water clouds that experience lightning storms and massive convection. These layered cloud decks interact in complex ways, shaping both short-lived phenomena and long-term structures. Regions known as hotspots reveal breaks in the cloud layers where infrared radiation escapes more readily, providing windows into deeper atmospheric levels. These hotspots correspond to downdrafts where dry air descends, suppressing cloud formation. Understanding these features helps scientists interpret similar phenomena on exoplanets, where cloud signatures often dominate atmospheric spectra. Jupiter's role as a laboratory for magnetospheric physics cannot be overstated. The interactions between the planet, its moons, and the solar wind generate one of the most active magnetospheres in the solar system. The enormous magneto-tail stretches millions of kilometers downstream from the Sun, sometimes reaching the orbit of Saturn when compressed or extended. This magneto-tail hosts currents, charged particles, and dynamic structures that respond to both external and internal drivers. The coupling between Jupiter's rotation and its magnetosphere produces phenomena not seen elsewhere, such as rotation-driven auroras that persist even when solar wind input is low. These auroras pulse with internal rhythms tied to the planet's rotation and magnetic anomalies, revealing the deep connection between the interior dynamo and the surrounding space environment. The synergy between Jupiter and Io offers an example of electromagnetic interaction on a planetary scale. As Io orbits within Jupiter's magnetic field, it generates electric currents that flow along magnetic field lines into Jupiter's atmosphere. These currents produce intense auroral spots, fixed glowing points corresponding to Io's magnetic footprint. Similar footprints from Europa and Ganymede also appear, though less intense. These features help scientists trace magnetic field lines and understand the structure of the magnetosphere. The constant flow of material from Io's volcanoes into the magnetosphere creates a plasma torus that influences radiation levels, energetic particle behavior, and auroral morphology. Radiation levels around Jupiter are extreme. Energetic electrons and ions trapped in the magnetic field can damage spacecraft electronics and pose challenges for mission design. Understanding these radiation belts has practical implications for future exploration, particularly for missions targeting Europa or Ganymede that may need to navigate harsh environments. Radiation also affects the surfaces of Jupiter's moons, altering chemical compounds and darkening ice over time. On Europa, radiation interacts with surface ice to create oxidants, which may eventually cycle into the subsurface ocean and provide potential energy sources for life. The balance between destructive and constructive effects underscores the complexity of Jupiter's influence across its system. Europa's ocean remains one of the most tantalizing mysteries in the search for extraterrestrial life. Beneath its icy shell lies a global saltwater ocean with more water than all of Earth's oceans combined. Tidal flexing induced by Jupiter's gravity keeps the ocean warm and stirred, potentially creating environments where chemistry relevant to life could occur. The surface of Europa shows evidence of recent geological activity, including cracks, ridges, and chaotic terrains that may indicate ice-ocean exchange. If plumes of water vapor exist, spacecraft could sample them directly, analyzing chemical signatures that might hint at biological processes. Europa thus stands at the intersection of planetary science and astrobiology, a testament to Jupiter's ability to nurture environments far from the warmth of a star. Ganymede offers a different but equally fascinating story. As the largest moon in the solar system, even larger than Mercury, Ganymede possesses its own magnetic field, an extraordinary feature for a moon. This magnetic field interacts with Jupiter's, creating a complex electromagnetic environment. Ganymede's surface shows a mix of ancient cratered regions and younger grooved terrains that hint at tectonic or cryovolcanic activity. Beneath its icy crust lies a layered interior with a probable subsurface ocean. The presence of a magnetic field implies a liquid, metallic core, suggesting a dynamic interior that continues to evolve. Ganymede serves as a comparative laboratory for understanding planetary differentiation and magnetic field generation. Callisto, heavily cratered and seemingly geologically inactive, presents a contrasting end member in Jupiter's moon system. Its surface appears ancient, preserving a record of early solar system bombardment. Yet Callisto may also harbor an ocean beneath its icy crust, though less dynamic than Europa's. Its lack of strong tidal heating due to its distant orbit means it experiences a more static evolution. Callisto's relative stability offers insights into how bodies evolve without significant tidal influence, providing important comparison points within the broader context of icy worlds. Io Europa, Ganymede, and Callisto form a progression of tidal heating and geological activity demonstrating how distance from Jupiter shapes moon evolution. This gradient reflects a fundamental principle. Proximity to a massive planet influences internal heat, surface conditions, and potential habitability. The diversity of environments within a single moon system underscores the richness of planetary science and highlights the importance of exploring multiple worlds to gain a full understanding of planetary processes. Humanity's fascination with Jupiter extends from mythological symbolism to cutting-edge exploration. In mythology, Jupiter represented kingship, authority, and cosmic order. In reality, the planet embodies these qualities through its physical dominance and dynamic presence. It is a ruler not by divine decree, but by gravitational might, orchestrating the motion of moons, asteroids, and comets. As telescopes improved, each new discovery added layers of complexity, transforming Jupiter from a distant dot of light to a richly detailed world of storms, magnetic currents, and diverse moons. Modern science continues to peel back layers of mystery, yet each answer generates new questions. What lies at Jupiter's core? How do storms form and dissipate deep within the atmosphere? How stable are the belts and zones over centuries? What triggered the dilution of the core, and what does it reveal about early planetary collisions? How do the oceans of Europa and Ganymede evolve over time, and could life emerge or survive in such alien oceans? These questions fuel ongoing missions and inspire future endeavors. Upcoming spacecraft will extend humanity's reach into Jupiter's domain. Advanced instruments capable of penetrating ice, measuring magnetic fields with greater precision, and analyzing atmospheric composition at unprecedented depth will refine our understanding. Missions designed to orbit or land on moons may uncover evidence of geological processes or even biological signatures. With each technological leap, the boundary between imagination and observation narrows, bringing the distant worlds of Jupiter's system into clearer focus. Yet Jupiter's story is not solely one of scientific inquiry. It also shapes perspectives on Earth and our place in the cosmos. By studying Jupiter's dynamic weather, we gain insight into atmospheric physics applicable to Earth and other planets. By examining its magnetic field, we deepen our understanding of magnetic shielding, crucial for habitability. By exploring its moons, we consider the possibility that life may exist in environments radically different from our own. Jupiter thus becomes a mirror through which we reflect on fundamental questions. What conditions foster life? How do planets evolve? What role does our world play in the vast network of celestial systems? As humanity continues its exploration of Jupiter, the planet remains an icon of cosmic grandeur. Its swirling clouds, powerful storms, distant moons, and unseen depths evoke a sense of awe that transcends disciplines. Whether viewed through a telescope, studied through spacecraft data, or imagined in artistic renderings, Jupiter inspires curiosity and wonder. It stands as a reminder that the universe is vast, dynamic, and filled with mysteries waiting to be uncovered.